I want to give a slightly different story on the search for these strange new particles from what previous speakers were talking about. And it was alluded to that type of experiment in Shankar's talk. So as Shankar pointed out, when we transit from trivial superconductor into the topological superconducting state, these two states at the end of the Y at exactly zero energy appear, and one should see zero bias anomaly. And that's what you've seen experiments in the previous few experimental talks where the search for these particular signature of Majorana fermions was conducted. There is another interesting property of a topological superconductor, which comes from the modification of the spectrum. So in a trivial superconductor, if we measure Josephson current, it follows the regular Josephson relation with 2 pi periodicity, while a topological superconductor, when we have these zero energy states, this fundamental Josephson relation is changed by the factor of 2. So the periodicity should be 4 pi. So it has been suggested that if one would measure these pi periodicity, that actually may be a strong indication of the formation of Majorana fermions. And that's exactly what we've been trying to do in our experiments. So in previous works, in previous talks, both Leo and Modi were talking about wires, which were CVD grown. We took slightly different approach. Namely, we start with a two-dimensional gas and fabricate wires from a two-dimensional gas. What it allows us is the following. We want to have, in order to be in the topological mode, we have to have Zeeman energy larger than the gap and the Fermi energy. In order to protect superconductivity, we should have a spin orbit at least as strong as Zeeman energy. Now, in indium antimonide, not only Rajba is a strong spin orbit part of it also has a very large Driscoll-Haus term, which does have this strange and fascinating texture, but also if you look at the strengths of spin orbit interaction of Driscoll-Haus term, it is proportional to the k in the quantized direction. So it will be inversely proportional to the square of the thickness of the wire. So if we have a thick wire, like CVD grown wire of about 100 nanometer, you will get spin orbit interaction, which will be about 0.1 times k in these units in MeV. That's approximately what Rajba also gives in 100 nanometer wide wires. That's approximately similar strengths of the spin orbit interaction. However, if we can reduce at least one dimension of our wire by a factor of 5, we can increase the strengths of spin orbit interaction by a factor of 25. So what it does is, that allows us, having smaller these dimension thickness, we can have much larger spin orbit interaction. So we can afford larger Fermi energy and still satisfy this relation. So we can actually move away from localization in these wires a bit. So what we actually do, we started with heterostructure, which is grown on gallium antimonide substrate. So then there is a big graded buffer, the barrier, and this indium antimonide wire slab, which is 20 nanometers thick. So what we do next, we do e-beam lithography. We pattern wire with a bit of an undercut. And we sputter niobium. When we do sputtering, although primarily we have niobium right in this opening, it also scatters to the sides a bit. And it will be important for our fabrication. So this thin layer of niobium, about 4 or 5 nanometers, can serve as a mask for further wet etching processing. So we can actually etch semiconductor, which now will have a shape of these niobium wire. When we expose niobium wire to ambient conditions, it's oxidized, and I will show you that this thin layer around the niobium wire is fully oxidized and becomes an insulator. So if we look now in the direction perpendicular to this board, actually if we have a small gap between two wires like that, right, we would have, and still overlap of this thin layer, it will be oxidized. So the device, actually this is a schematic of our device, so we would have 2 niobium fingers. This gray area is just a continuous niobium which is oxidized and ambient, but that protects the semiconductor underneath. So semiconductor has a shape of this gray niobium oxide. And this is an FM micrograph of one of the devices. So this is niobium, this is niobium finger, and if you have a very sharp eye, you can see that there is a small halo around this wire. This is this oxide. This is before wet etching. Now, how we can prove that all our current actually flows through the indium antimonide, and it's not shorting through this thin niobium layer. We can make similar device just on semi-insulating gallium arsenide, and we can show that if we substitute this indium antimonide with semi-insulating gallium arsenide, our current between these two fingers will be blocked. So that's how our devices look like. So we do have, this is just a big micrograph. So we have multiple devices in a series, so we can gradually change gaps between the devices. This is AFM micrograph of one of the devices before etching, and this is after etching. And you can see that these halo it becomes a bit more pronounced. That's the extent of these oxide layer. So, and etching is fairly shallow. It's about 50 nanometers. So it's much smaller than the width of the wire, which is about 300 nanometer. So if there is a bit of underedge, which we expect it is, it's still not enough to completely eat up the semiconductor wire. And then we can apply DC and AC current on these electrode, and we ground the other electrode, and we can measure transport. So first, I would start with just these test device. So we have these 2 niobium fingers, and it's fabricated on insulating gallium arsenide. and you can see that for a continuous wire, so if we don't have a gap, we do see a very nice superconducting transition. So for this thin wire, it's around 2 Kelvin, and for wide region, it's about 7 Kelvin for our niobium wires. That's the cross-section of these wires. You can see that's the niobium in the middle, and these ears are the thin niobium layer which I've been talking about. Now, if we do have a gap, and that gap is larger than something like 30 nanometers, then transport through this wire is suppressed at low temperature, and the system becomes fully insulating. Now, if we take now a device, similar device, but fabricated on indium antimonide, then we again see a series of transitions which correspond to large areas. That's about this at 7 Kelvin. Then we do have these transition which corresponds to these narrow fingers, and then at lower temperature, we see transitions which correspond to the proximity effect in these Josephson junctions. And we can do some very simple estimates what's the induced gap just using simple BCS formulas. So if we do IV characteristic on our devices, we see very nice zero voltage region of induced superconductivity. What we also see that this nonlinearity at low voltages, if we replot this data as current versus voltage, what you can see at low voltages, there is enhancement of current. That enhancement is usually attributed to the Andreev reflection, which is a coherent process, and Andreev reflection is something which we should see in order to have bound Andreev states. And we do have this enhancement of conductance at low voltages, and you can see that if we apply in-plane magnetic field, that enhancement persists up to about 4 Tesla. Now, if we apply magnetic field to just a continuous wire, what is plotted here is differential resistance. So here we have zero resistance state. On this plot, all scans are done from negative to positive current. So we do have this is critical current, this is return current, which for just continuous wire, we have very large difference between a critical and return current. We can look how critical current changes with magnetic field. At low fields, it changes approximately following this equation, which gives us the first critical field of about 2.5 Tesla. And we do see zero voltage states up to about 5 Tesla. In a Josephson junction, as we can see, these zero voltage range also persisted to about 5 Tesla. Now, what we measure? Josephson effect. The direct Josephson effect, if we have two pieces of superconductor, we separate it by a weak link or an insulator, then there is a phase develops between two superconductors, which is not a constant but changes in time, and that change is proportional to the applied voltage with these two fundamental constants, and that is basically our fundamental, the gold standard of voltage. Now, there is an inverse effect which also exists. So if we have our two superconductors and we apply current, but now current has both DC and AC component, then there will be a voltage developed across this junction, and voltage steps will be again proportional to the frequency and the fundamental constants. and these constant voltage steps are called Shapiro steps. That's how they look like and that has been sort of known since way before I was born. So at zero field, that's what we measure, right? If you have 2 gigahertz frequency on top of DC current, then you expect steps to be separated by 4 microvolts. These green lines are 4 microvolt apart, and you can see that steps follow that pretty nicely. If you have 3 gigahertz, it should be 6 microvolt apart, and you can see steps with these 6 microvolt separation. If we apply 4 gigahertz, it should be 8 microvolt, and you see steps with these 4 microvolt separation. Now, this is not a full story. You may ask me what the correct question, what power, RF power is that taken at. So before I tell you that, I would replot my data from just IV to differential resistance versus current. So these peaks will correspond to transition between the plateaus, and minima will correspond to plateau Shapiro steps. So as you can see, if I change RF power, there is a whole X-ray of our chest here. So these black regions are different Shapiro steps that would be 0, 1st, 2nd, 3rd, and so on, so forth. That's where the current, the step in current appears. Now one can extract the widths of these plateaus as a function of power. At high power, it should follow the Bessel function. For the nth plateau, it will be nth Bessel function, and you can see that it follows it pretty reasonably. Okay, so that that's what we see. Now, if we start applying magnetic field, what we see that at zero field, we have all the steps at 1 Tesla, at 1.6 Tesla, we see all these steps. At high field, this step vanishes. And if we want to investigate it in more details, this is from 0 to 3.5 Tesla. You can see that step at 12 microvolt, which is the second step at zero field, persists everywhere till we can see Shapiro steps, while step at 6 microvolt vanishes at about 2 Tesla and does not reappear further. So if we do have phase transition, we should have closing of the gap. What we see that at 2 Tesla, there is a reduction of the critical current. Here we do measure critical current, not the gap. So we expect that we do have several just regular non-Majorana channels in our system. So we expect that density of gapless excitation is small compared to the gapped ones, and that may result in these non-zero critical current, although gap is closed. Now the question, the other question I need to just 2 minutes. Nope. Okay. Okay, very quickly, is it 2 pi or 3 or 4 pi periodicity? So if one measures it at constant voltage, one should see both 2 pi and 4 pi. Although the group of Gloria Platera have shown that if you have constant current measurements, then odd steps do vanish even in the presence of the non-Majorana supercurrent, and they actually calculated what should be the step widths in this case, and that corresponds to what we see in experiment. So, and finally, I just want to mention that we see vanishing of the first step, but not on the third and highest steps, odd steps. So there is a crossover from low power regime, where we do have more or less linear system, to high power regime when it becomes very nonlinear. And the first step corresponds to this power. So we are in linear regime already. The third step in a very nonlinear regime. So if we take another sample where our critical current is much smaller, then that sample may fall completely into the nonlinear regime. So the first step would be way in the nonlinear regime. And indeed, if we have sample where critical current is 10 times smaller, so our RF power is much larger than this crossover, we do not see vanishing of the first step. And that's sort of something similar Sega Tarucha has been presenting a couple of days ago. So I guess I need to finish, and I'm finishing. That's our results, and I have much more information in the appendixes to this paper.
Thank you very much. I'm afraid unless I really see somebody waving very, very vigorously, then we don't have time for questions after this talk. Not very vigorously. Because we really have to, maybe while Professor Marcus is hooking up his computer, maybe you can ask a question.
It's a question about the origin of spin-orbit interactions. So in your system, you don't have electric field, so it's probably Drexel house.
Yes, yes. It's from my estimate, the Drexel house in my system is much larger. It is much larger than, it's about a factor of 10 larger than in the experiments of Leo, if I would just put numbers. So that allows me to work at much higher magnetic field. So I can use 3 Tesla instead of 0.3 Tesla, which he uses in his experiments.